Well, thank you very much. Thanks to the organizers for inviting me to this very nice workshop here. Yeah, so in the following I'm going to speak about the competition between quantum spin tunneling and Kondo effect. So basically, this work done in collaboration with Joaquim Fernandez Rossier at the INL in Portugal. And so we are basically combining two obsessions here. So Joaquin's obsession is quantum spin tunneling, one of your obsessions maybe only. My obsession is Kondo effect, and we have combined these two obsessions into this work. So Cyrus already introduced you to the concept of inelastic spin tunneling spectroscopy in his beautiful lecture. So I'm just going to briefly remind you about it. About the main concept. So when you, as they did in their original work here, measure iron, for example, on the copper nitride substrate, you see these with an STM. So you measure the spectra with an STM. You see here these steps occurring at finite bias voltages. And in this work, they realized that these inelastic steps here in the STM spectra, they correspond to spin excitations of the iron atom, which can be described by this phenomenological Hamiltonian, spin Hamiltonian here, which has in a phenomenological way magnetic anisotropy included here. So here you have some the dominant axial anisotropy D, and this is the in-plane anisotropy E here. And so the excitations of this Hamiltonian correspond to the positions of these, or the eigenvalues of these Hamiltonian correspond to these steps here in the inelastic tunneling spectra. And and when you calculate in perturbation theory, Fermi's golden rule, you can even reproduce quite fairly these spectra here. So iron is a spin 2, and so it's an integer spin. And what integer spins have is can have is the so-called quantum spin tunneling. So so quantum spin tunneling occurs on atoms or molecules. Cyrus always says not forget about the molecules, so I've done so here, with integer spin, and when you have a negative uniaxial anisotropy. In this case, the ground state of the atom or molecule is doubly degenerate and consists of the highest spin projections of the of the highest of the states with the highest spin projections. Now, so you can switch between the two ground states by either thermally exciting via this staircase here, or by quantum tunneling. And one way to do this is via if you switch on in-plane anisotropy. So what this does is that lifts the degeneracy of the ground states, splits it. So the ground state is now a linear combination of the two original spin states, and this splitting between the ground state and the excited states, this is basically the quantum spin tunneling. So basically, when you now put your system into a spin eigenstate, it will tunnel. So it can tunnel to the other spin state with the opposite spin projection via this quantum spin tunneling. So basically what will happen is that Rabi oscillations occur and the system oscillates back and forth. So this basically quenches the spin of the atom or molecule, this quantum spin tunneling mechanism. And well, we know also another mechanism which frequently occurs in atoms and molecules deposited on conducting substrates that quenches the spin is the Kondo effect. So the Kondo effect can always occur as soon as you put some magnetic atom or molecule on a conducting substrate. And a simple model that describes the Kondo effect is the Anderson impurity model. There you have a single strongly interacting impurity level which is coupled to a bath of conduction electrons. In the situation where this impurity level is singly occupied, you have a spin associated with the impurity, but by these hopping processes which are depicted here in this cartoon, the spin can flip. And these spin flip processes become very important at low temperatures, and they lead to the formation of a new ground state where the impurity spins forms a total spin singlet state with the surrounding conduction electrons. And so by this by the formation of this Kondo singlet state, the spin is effectively screened. And another important consequence is that this leads to the formation of a zero bias anomaly, the Kondo resonance, just at the Fermi level, and the density of states of the system. Okay, and the width of this Kondo peak is roughly the Kondo temperature given by the Kondo temperature, which is the critical temperature below which the Kondo effect is observed. So this Kondo peak can be measured by STM spectroscopy, and depending on now whether the electrons tunnel directly through the resonance or only directly to the substrate, or a combination of those, you can observe different line shapes. So here's an example for cobalt on kappa substrates. So here you observe this asymmetric line shape. This indicates that the tunneling occurs both directly through the Kondo resonance as well as directly through the substrate. So you have, due to quantum interference, you have formation of this asymmetric line shape. And if the tunneling is only directly through to the substrate, then you will have a dip in the DIDV. And on the other hand, if you only tunnel directly through the Kondo resonance, you will have a peak. And so this is well described by this Fano formula, which just describes this. So this is basically taking into account the quantum interference between different tunneling paths of the atom or molecule. So often one thinks of half-integer spin systems when thinking about the Kondo effect, but the Kondo effect also occurs in integer spin systems, and the good example is just this. Cobalt on the kappa substrate, on the naked kappa substrate, is a spin 1 system actually. Here, so Kondo effect and ISTS steps, inelastic spin tunneling spectroscopy steps, here have been also observed jointly, right? In one system, this is an example of cobalt on the kappa nitride surface, right? And so here, this is basically again described by this effective spin Hamiltonian here, and we have a spin 3½ now on the cobalt in this case, and for positive D, you get this splitting by the magnetic anisotropy of the spin states, where the lower doublet is basically the spin plus minus 1/2 projections, right? And these are the ones that give rise to the Kondo effect, and excitation to the higher doublets give rise to this inelastic step. And when you now apply a magnetic field, you split these doublets, right? And you get and the Kondo peak, for example, splits. So in the following, I'm going to show you that for integer spin systems that have quantum spin tunneling, something similar happens. Just that instead of the splitting occurs with the magnetic field, it's basically the quantum spin tunneling that splits the ground state doublet. So how am I going to do this? So I'm using an Anderson model which has the magnetic anisotropy incorporated in it in a phenomenological way. So we have basically an Anderson model which consists of the Hamiltonian of the atom, the Hamiltonian of the substrate, and the hybridization between both. And the atom Hamiltonian is here just these impurity levels. This would just be a normal Anderson model. Here we have with several levels, so it's a multi-orbital Anderson model. Here's Coulomb interaction, and here's Hund's rule coupling, which makes the system prefer the high spin states. Okay, and here the term that describes magnetic anisotropy is just this spin Hamiltonian, which I have introduced before. Now here, this is the substrate electrons. These are just non-interacting conduction electrons, and this is the coupling between both subsystems, the hybridization. Now, when we integrate out the conduction electron degrees of freedom, we end up with a so-called hybridization function, which describes basically the coupling of the electrons in the impurity in the atom to the conduction electrons. So the imaginary part basically is of this hybridization function is the broadening of the atomic d levels due to the coupling to the substrate. And so here in the following, so I'm going to assume simply that this hybridization function is constant, so it's not energy dependent, and it's the same for all impurity levels. Yes?
I have a question. These spin operators, are they completely different degrees of freedom from the electron?
No. They act on the electronic spectrum.
So they are expressed in the electron operator?
Yes. Yes. And further on, I assume these interaction parameters, so the Coulomb repulsion between electrons on the atom is, I just assume 4. Just should note that the important quantity is basically gamma over u, and I will vary gamma in the following. So, quite high Hund's rule coupling, which is near to typical values of 3D transition metal atoms. And now I have to solve this problem, and what I'm using is the so-called one-crossing approximation. So I start with a diagonalization of the exact diagonalization of the atomic Hamiltonian. This gives me the many-body eigenstates of the Hamiltonian, and I introduce so-called pseudoparticles, which correspond to these many-body eigenstates of the atomic Hamiltonian. And I impose commutation and anti-commutation rules on these pseudoparticles, and this allows me to use the machinery of quantum field theory to solve this problem. So I can now express basically, I can write down the propagators corresponding to my many body states as normal propagators for fermions or bosons. Right, so this is basically given in terms of the eigenenergy of the corresponding many-body state, and this is self-energy basically describes the coupling to the substrate, the coupling of the many-body state to the M to the substrate. And now what I do is I do an expansion in the hybridization function for the self-energy. And these are the diagrams basically one takes into account. And so the simpler approximation is the non-crossing approximation, which consists only of those diagrams. It's an infinite resummation of diagrams of this type. Okay, and if I take into account also these crossing diagrams, this is called the one-crossing approximation. So this has to be solved self-consistently, and once this is converged, I can calculate from the pseudoparticle propagators the real electronic quantities, for example, the spectral function, by convoluting these pseudoparticle propagators. So here is, Cyrus already showed that in his lecture. So here we applied basically this technique to describe the experiments of cobalt on copper nitride, and you can see that we could fairly well reproduce this moving of the inelastic steps inwards when the coupling to the conduction electrons is increased, and simultaneously the Kondo peak increases, right? Just as is observed in experiment. So now I want to apply to integer spin systems. So let's start with spin 1. How is that? So here is so for negative uniaxial anisotropy, you have this diagram for the states. So here the ground state is doubly degenerate, consists of the m equals -1 and +1 spin projections, and now the in-plane anisotropy introduces a splitting between those, right, and gives rise to this quantum spin tunneling here. This is a splitting, and which is basically the quantum spin tunneling given by 2e. Yeah, so now here you see a spectrum for, I've just taken some parameters which actually, well, more or less correspond to having inelastic steps at the position where you would have the cobalt, in the case of the cobalt atom. So it's basically they are at 10 milli electron volts here. Okay, and you get this very typical step-like spectral function here for these chosen parameters. So with a finite in-plane anisotropy. Now, when I switch off the in-plane anisotropy, I get actually a Kondo peak here at 0 bias. And so how can this Kondo peak actually occur? So you need to get from the -1 state to the +1 state, and this can occur actually only via this intermediate by hopping to the intermediate m equals 0 state, which is at 10 millielectron volts with respect to the ground state, right? And so this Kondo effect is suppressed basically to the in comparison with the Kondo effect in the spin 1 system without magnetic anisotropy by this factor J over D, we think, where J is basically the Kondo exchange coupling of the system, which you get from, which is basically gamma over the Coulomb interaction, gamma over U. Okay, so here is so here we see how the effect of decreasing E. So we start here, the red line. So we have finite E, and we now slowly decrease E, and we see that this gap becomes smaller, moves to low energy, and also these here this bending of the upward bending increases when we decrease E, and basically here we could speak of what is something like the split Kondo state, which is also observed when you apply to the normal Kondo system a magnetic field, right? And yeah, and finally the splitting disappears, and you have a simple Kondo peak. You can play the same game with gamma, so the coupling to the conduction electrons. So basically, so starting here with some finite magnetic anisotropy, we have here our small gap at 0 bias, and so we increase gamma, and the same thing happens. So while, and actually here also note that here the step corresponding to the second excitation energy moves to lower energy, just as in the case of the cobalt on copper nitride. This is basically the renormalization of the excitations of the magnetic anisotropy by the exchange coupling. Okay. So here we draw basically the effective quantum spin tunneling as a function of gamma, the coupling to the substrate. See here, we start here with the bare gamma here, and as we increase gamma, with the bare delta zero, the bare quantum spin tunneling, as we increase gamma, this decreases, and until at some point it completely disappears, and that's when we can get Kondo effect. So the quantum spin tunneling has been renormalized to an extent that these the previously split states are now effectively degenerate. Okay, so when we apply a higher in-plane anisotropy, actually we don't get exactly the same behavior. It also decreases the quantum spin tunneling, the effective quantum spin tunneling with the coupling, but we never reach the point where we get the Kondo effect before actually the system is not really any longer in the local moment regime. So we don't have formation actually of a spin on the impurity. Here's again showing the temperature dependence. So starting at high temperature, you first have here kind of a bump here, and then you lower the temperature, you see that there's a splitting, and this splitting gets deeper when you lower the temperature. And one thing I got worried yesterday about was in Marcus' lecture was actually he also had a spin 1 system, this cobalt on boron nitride, right? And also with negative magnetic anisotropy D, and they never have these, nor in the experiment nor in his perturbation theory, this upbending of the inelastic step. So I wondered. So here you see it actually, right? So here you have a flat, basically flat step, and here including a downbending. So I wondered, oh my God, I've never seen that. So how could that be? So then I realized that actually what they have in their system is a very large in-plane anisotropy. And so yesterday I ran a calculation with these parameters, I also get here this down for this temperature I get a downbending here, and which becomes flatter, and maybe even eventually will show a slight bending up when you lower the temperature. So maybe this is also an indication that this is basically also weak coupling, and when you go to strong coupling by lowering the temperature, you also again will get some kind of small upbending. So here this is to show that charge fluctuations can have a similar effect as increasing the coupling to the conduction electrons. So because they also charge fluctuations also increase the Kondo exchange basically. And here you see, so this is the particle Hose symmetric case. Now I shift up the impurity levels in energy, so they are the impurity is emptied a bit, and you see that it gets a bit more asymmetric, and also there's this upbending occurs and a slight renormalization, and here when it's very strong you get again this split Kondo feature and the strong moving of the inelastic steps at higher energies. So here's also I was going to show, well, I can go quickly over it in 1 minute, so that's the same for spin 2. Here, there the ground state is this doublet m plus minus 2. And so here I took the parameters for iron on copper nitride. And you see here for low coupling, you see basically something very similar to what Cyrus measured in his experiment 2007, right? These steps. And again, as I increase this, so the steps move inwards to lower energies, and this is slowly converted into the lowest step is converted into a split Kondo feature. Yeah, so here, also here you have an effect of charge fluctuations, right? They make the system, the spectra slightly asymmetric, and also drive the system towards Kondo effect. Yeah, so that's it. So basically we have seen, so quantum spin tunneling and Kondo effect, they compete with each other. Kondo effect actually leads to a renormalization, or not Kondo effect, I should say. Kondo exchange coupling leads to a renormalization of the quantum spin tunneling. And so when the Kondo coupling becomes very strong, the quantum spin tunneling is suppressed and we get a Kondo effect. In the intermediate regime, where the Kondo, basically the Kondo temperatures of the same order as the quantum spin tunneling, we can get these split Kondo features at zero magnetic field. And charge and valence fluctuations can also drive the system towards Kondo behavior. And this is now on the archive. And well, thank you for your attention.